so let's talk about recursion in Java. It's one of those things that can feel really powerful, but also kind of mind-bending, right? Well, today we're going to pull back the curtain and demystify it so you can confidently add this amazing tool to your programming arsenal. All right, let's start with a really simple, almost weird question. What if a function could call itself? I know, it sounds like a loop that would never end, maybe even a mistake, but this one idea is the key to a whole different way of solving problems. I mean, just look at this pattern. It seems incredibly complex, almost impossible to describe. But what if I told you it's all built from one single repeating rule? A rule that applies to smaller and smaller versions of itself. That right there is the heart of recursion, building beautiful, complex things out of simple, self-repeating steps. All right, so what is recursion at its core? To really get it, we're not going to start with code. Nope, we're going to start with a super simple real-world analogy that makes the whole concept click.
Okay, picture this. You're stuck in a gigantic line, so long you can't even see the front. How do you figure out what number you are in line? Well, simple. You just ask the person in front of you. Of course, they probably don't know either, so what do? They ask the person in front of them. This chain reaction continues all the way up until it reaches the very first person in line. And that person, they know the answer directly. I'm number 1. They tell the person behind them, who can now figure out they're number 2. And that answer works its way all the way back down the line until it finally gets to you. You solved a huge problem by just breaking it down into smaller, identical problems. And right there, in that simple story, we've actually uncovered the 2 essential parts of every single recursive algorithm. First, you've got the base case. Think of this as the stopping point. It's the simple problem we can answer directly, like the person at the front of the line who just knows they're number 1. Then you've got the recursive case. This is the part that breaks the problem down, the step that says, I'll solve my problem by asking for the answer to a slightly smaller version of the same problem. You know, asking the person in front of you. You need both of these for recursion to work. Okay, theory's cool and all, but let's see what this looks like in actual Java code. We're going to translate our person in a line idea into a classic programming example that you'll see everywhere. Okay, check out this code for calculating a factorial. This is a classic for a reason. See that if n less than or equal to 1 part? That's our base case. That's the person at the front of the line who knows their number is 1. It's the simple, direct answer that stops the chain. And then the else block. See how the fact function calls itself but with a smaller number and -1? That's our recursive case. That's the code equivalent of asking the person in front of you for their position. So let's walk through this. What happens when we call fact of 3? Well, the function doesn't know the answer right away, so what does it do? It calls fact of 2. And fact of 2? Same problem. It doesn't know, so it calls fact of 1. And boom, we hit our base case. Fact of 1 knows the answer is 1, so it returns it. Now the whole process unwinds. Fact of 2 gets that 1 back, calculates 2 times 1, and returns 2. Finally, fact of 3 gets the 2 back, calculates 3 times 2, and returns our final answer, 6. Okay, so that whole unwinding thing, where the function just seems to remember where it was, that can feel like straight-up magic, but it's not. There's a very real mechanism inside the Java virtual machine that makes it all happen. So let's peek behind the curtain. And hey, if you're thinking, wait, how does it do that? You are definitely not alone. This quote from a learner on the Free Code Camp forum says it all. How is the n value not lost? It's a #1 question people have when they're learning this stuff. The secret is something called the method call stack. And honestly, the best way to think about it is like a stack of plates or boxes. Every single time a method is called in Java, a new box, they call it a stack frame, gets put right on top of the pile. And this box holds all the local variables and parameters for that one specific call. Let's watch this happen with our factorial example. Our main method calls fact of 3. Bam, Java puts a new stack frame for fact of 3 right on the stack. And inside that frame, as you can see, n is 3. Now fact 3 calls fact 2. So what happens? Another brand new frame for fact 2 gets pushed right on top. And the key thing here is this new frame has its own separate copy of n, which is 2. The frame below it is just waiting patiently. And you guessed it, it happens one more time. Fact 2 calls fact 1, and a third frame gets slapped on top, with its own n set to 1. See? This is how Java keeps everything straight. Each call has its own private workspace. Okay, now we've hit the base case. Fact of 1 does its thing and returns 1. Its job is done, so its stack frame gets popped right off the top. That return value, 1, gets passed down to the frame that's now on top, fact of 2,
which can finally finish its calculation. This just keeps happening. Frames pop off until we get our final answer back in main. See? No magic, just a really neat and tidy system. So what happens if we mess up? What if we forget that all-important base case? Well, look at this code. It calls decrement in print, which then calls itself, which calls itself. And there is literally nothing to tell it when to stop. And here's what happens. Remember our stack of frames? Well, with this code, a new frame gets added, and another, and the stack just keeps growing, higher and higher, until it literally runs out of space in memory. And that's when your program crashes with the infamous Stack Overflow error. If you look at the error message, it's a dead giveaway. You see the same line number over and over and over again. That's the signature of a recursion that's gone wild. Okay, so now that we get how it works and how it can break, the big practical question is, when should you actually use it? When is it better than just a simple for or while loop, what we call iteration? This table really breaks down the trade-offs. On one hand, iteration, your standard loops, is usually going to be faster and use less memory. Why? Because you're not creating all those stack frames every time. But, and this is a big but, for some problems, a recursive solution can be so much cleaner, so much easier to understand. Things like navigating a file system or complex data structures, they're just naturally recursive. So here's a really good rule of thumb. If you're building something where every nanosecond counts, maybe in game development or high-frequency trading, you're probably going to stick with iteration. But if your goal is to write code that's easy to read, easy to debug, and elegantly solves a problem that breaks down into smaller versions of itself, recursion is an amazing tool to have in your belt. But here's the thing. Recursion isn't just a fancy way to write a loop. It really starts to shine when you get to problems that are just a huge pain to solve any other way. So let's look at where it really flexes its muscles and a cool trick to make it even more powerful. A perfect example is the classic Tower of Hanoi puzzle. The goal is to move a stack of disks from one peg to another, with a couple of simple rules. Now, trying to solve this with a loop is a real head-scratcher, but the recursive solution is incredibly elegant. It basically says, to move a big stack of disks, you just need to know how to move a smaller stack of disks out of the way. It's a perfect example of a problem that's practically begging for a recursive solution. Okay, one last awesome trick. If you try to write a simple recursive function for something like the Fibonacci sequence, it's painfully slow, just awful. Why? Because it ends up calculating the same values over and over and over again. We can fix this with a clever technique called memoization. It's really just a fancy word for caching our results. We use something like a map to remember the answers we've already figured out. Before we do any work, we check the map. Is the answer already there? Great, just return it. This simple trick can take a function that would run for minutes and make it finish in a fraction of a second. So there you have it. We've seen that every recursive function has to have a base case and a recursive case. We pulled back the curtain on the call stack, the magic that makes it all work, and we've seen how it can offer these incredibly elegant solutions to really tough problems. Recursion isn't just a coding trick, it's a whole new way of thinking about problems. So now that the magic is gone and you see how it really works, how are you going to use it to solve your next big problem?